Are you done?
Yeah, of course.
Well, what is this?
These are some of the principal equations of electrodynamics. Electrodynamics just being electrons, electricity, dynamics, motion, things moving. So electrodynamics, how electricity moves. So what we've got here are Ohm's law in its usual form and Watt's law in its usual form. Now I'll preface right away and say that there is some contention as to whether voltage should be V or E. So I like V because that's how I was taught, but E does work very nicely down here because instead of PIV it would be pi, which is nice. So that would be easier to remember. But PIV is still okay.
Well, what do each of those letters mean?
Well, we have E or V, V in this case here, is voltage, I is current, and R is resistance. So V is equal to IR. That's if the voltage within an electrical circuit will be equal to the current within the circuit that's flowing through it times the resistance, the total resistance of that circuit. And then down here, the power of an electrical flow is going to be equal to the current, how much is flowing, times the voltage, which is kind of analogous to the pressure pushing that flow there. So let's talk about power first. Do that. So the power, we can think of it like this. You've got two water sources. One of them is a huge, huge river. There's a pretty large flow rate. The current in that is 50 gallons per minute, let's say. But because it's such a big river, those 50 gallons moving by every minute mean that it's a very, very slow flow. The voltage, or the pressure within that river, there's not too much of a pressure difference between one point and the next. So the flow moves slowly. It's still that same 50 gallons per minute current, but there's not too much power in that. Versus if you had a very, very, very tiny nozzle through which you were blasting 50 gallons per minute of water, then that current is going to be much, 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 much faster, given the same power. So,
Well, Mr. Coffey, in a river, water flows, but what about an electrical circuit?
it's the flow of electrons. So the current measures the flow of electrons. And there are some words that I can use here, like coulombs, and then coulombs per second would be amperes. And that refers to charge and the charge per second, which is similar to gallons like of water, and then per time. So a quantity per time would be a flow or flow rate of things. So in a circuit, the current I is the amount of charge, which is the number of electrons flowing past a point in the circuit per unit time. So the current flow of charge per time. And those charges are given by electrons. Now, electrons are kind of complicated because nobody has a fully clear and concise model of what they are right now. A lot of textbooks are still teaching incorrect models like the Bohr model, and hopefully nobody's doing Rutherford things and stuff like that. That's from far before that. But the most recent version of what an electron is a probability region that extends out into all of space. So that means that an electron cannot be known where it is. You can't know where the electron is until it is you observe it. And once you observe the electron, then you know where it is. Pretty self-explanatory. But this means around atoms, we don't think of them as little orbs revolving about the nucleus, like in the Bohr model. We think of them as a cloud of possibilities around existing in the s, p, d orbitals, all of those around the atom. So all of those floating there, that's what the electrons are. And then when you have certain kinds of atoms, namely atoms that have substances called conductors, that conductors are made out of, those have some extra electrons, so they share the electrons amongst each other, all those atoms within that conductive material. And so the electrons are free to move from one atom to the next. Actually, Bill Nye has a very good video on this, all on electricity, that I highly recommend if you can find it on YouTube somewhere. And concerning all the vocabulary in this, and other stuff too. There's an excellent TED talk called The Electric Vocabulary, which really outlines with some great animation all of the electric vocabulary, where it came from and why we have it, why we know these things as we do today.
Mr. Coffey, well, what is voltage?
To start that question, I'll say that electrons all have a certain charge to them, a negative charge. So that negative charge, you can think of it as almost like a magnet. We deal with magnets, so we know that if we take the north end of a magnet here and face it toward the north end of a magnet here, and try to move them together, we're going to feel them repelling against each other. They don't want to be next to each other. Same thing with negative charges, like electrons. If you have these negatively charged little subatomic particles there, and you try to scrunch them toward each other, they're going to feel a force of repulsion away from each other. So a voltage, which is the electromotive force, or what moves the electrons, arises because certain mechanical processes or thermal processes or other forms of energy transfer into the circuit, like electrochemical, whatever. They're pumping electrons all to one side of a circuit or one side of a conductor. And when all of the electrons are scrunched together like that, it's like a whole bunch of super balls being packed together, very, very, very tight. If you give them a path outward in electricity, that's through a conductor, then they're all going to want to flow along that path out of where they're being packed together. So the voltages arise as a result of smushing all these electrons, which do not want to be next to each other, together. And then they want to move. So if you scrunch them tighter, there's a higher voltage. They want to move a whole lot more to get away to reach an equilibrium where they all have a nice equal voltage. So what batteries do within a circuit, if I might draw, let's say that you have a battery in a circuit. And I'll throw a resistor in here. The battery is going to pump electrons from the positive side. There's really a carbon rod in the middle, or a graphite rod, and then it's surrounded by maybe a zinc can. And then there's an electrolyte in here. Electrons are being pumped down to this side of the battery. And when they're all packing up over here on this side, because when you have an absence of negative charge, because they're all being pumped from this side, you have a resultant positive charge over on this side. So all these charges want to balance out with the positive, so they're going to flow through the circuit, through the resistor, or up and around to the positive end, where they can balance out with those charges. Now, if you have an electrochemical cell like a battery, it's just going to keep on pumping those charges to that side. So you're going to get a direct current through the conductor. Okay, so here are our three variables that we know from Ohm's law up here. If we have the voltage V being generated by the power supply, the current flowing around it, I, and then a resistor, R, very simply we can say that Ohm's law will provide us with the answer to any one of these values given the other two. So if we need to find voltage, we use this one right here, current times resistance. If we need to find current, we use voltage divided by resistance. If we need to find resistance, we use voltage divided by current. So you notice that voltage is in the top here, and that's just because when we have the voltage is equal to these guys times each other, then we're going to divide by one or the other to make it happen, which is great. Algebra. So voltage is measured in volts. Current, color coordinate this, is measured in amperes. Amps. And then resistance is measured in ohms. abbreviated with the Greek letter omega. So to solve for any given one of these, just find the other two values, and you can solve for it. I'm not going to do the algebra.